All right. What I'm going to be doing right now is hoping to have a relatively short video to better um, fill out my lesson that I provided on circular motion along a vertical plane. Um, I did cover some in class, which was the classic example of something being whipped in a vertical plane, like a bucket that has water in it. You tie a rope to it, and then you can rock it back and forth, and then eventually start to swing it like this around. And this is a very classical question in this topic. Often, there's many other questions that also come into play, but many times it's the one of the leading questions is, what is the minimum speed in meters per second? What is the minimum speed that the bucket has to have at the top of the path so that the water doesn't spill out? Because if you do this fast enough, and I hope to do it for you in a class coming up soon, so I have all the setup for that to do that. I've done it before and it works fine, as long as it's moving fast enough. There is some minimum speed that it has to have at the top so that you can be guaranteed by the laws of physics that water won't spill out. If you're moving it in such a way where the speed at that top point is a little bit slower, even anything slower than that minimum speed, it will spill out. I'm going to address that with you now if I could. We'll just have to shut off my camera here. Pull this one up. And let's see, camera. All right. So as I showed in class, if you are zipping something around, or actually what I showed in class was just a pendulum rocking back and forth like this, and we had a mass tied to the bottom of a string, and the string was tied to my ceiling, and then I had the force sensor here with a little hook on it, and it was measuring how much force of tension, essentially, was being applied to this block as it went back and forth. And we saw that the tension actually varied. When the speed was greatest, which was down here, and it's got to make a little wind to make it look like it's moving fast. When the speed is moving fastest at the bottom, the centripetal force, which always points towards the center, is at its maximum. This is the centripetal force. And when V is at a maximum value, it slows, stops, speeds up, maximum speed, slows, stops. The maximum speed is at the bottom. Then when V is maximum, the centripetal force, which is the tension, is the maximum. So you get a lot of upward force at the bottom. It turns out that the amount of upward force at the bottom is always going to be more than what you weigh. So again, if this thing just stopped entirely, and in class I had done used a 1 kilogram mass, then we saw that the force sensor, when it read out, what it read out was 10 newtons, because m times g is 1 times 10 is 10 newtons, right? But as this thing then goes back and forth, there's an extra amount of force necessary to be in the upward direction equal to this, right? The net force in the forward direction towards the center has to be equal to mv squared over r. So if we already have a weight force that's down of 10 newtons, let's just say, and let's just say that at the bottom it's going to be moving. Actually, when I think about it, I think we had a speed when we calculated it for the rope problem that I did with you guys. Someone jumping from a hill, rope swing kind of example. But let's just say that the speed at the bottom was 10 meters per second. Let's just say. And let's just say it's, like we said, a 1 kilogram mass. Then we'd end up with 1 times 10 squared divided by, and how convenient, let's just call it 1 meter. Let's call the length of the string is r, right? This is a giant circle here. And r, the center of the circle, is here. So r, let's call it 1. Doing mv squared over r, what would I get? 1 times 10 squared over 1. So I get 100 newtons, right? So what that means is if this thing is going to be moving with this speed of 10 meters per second in this direction at the bottom, it needs to feel an upward force of 100 newtons. If gravity is pulling down with a force of 10 newtons, then how much upward force do we need so that the net force comes out as 100. That means I won't draw it that long because that would be crazy long, but this amount would have to be 110 newtons, and that's the tension. And the tension in the rope would have to be 110 newtons. Subtracting away gravity, which is 10 newtons, provides us with a net force of 100 newtons. And this thing will be fine. It will stay, it won't break, essentially. The rope won't break, and it won't go flying off in some other direction. It will stay on that curvature path that has that curvature at that moment, as long as that can be satisfied. That amount of centripetal force can be met by the tension in the rope, right? So that's just me reminding you of that. Now think about this thing now going all the way around, right? All the way around. Now you can swing it at any speed you want, obviously, but often they're wondering, what is that minimum speed? So again, let me just remind you, the tension is more than it weighs, right? This is 11 times its weight, right? This tension force is 11 times greater than what it weighs. And no matter what the speed is, no matter how slow this thing moves, the upward tension will always be more than it weighs. Because even if it was 10 newtons down and I put in some decimal here, like some small speed, just barely going back and forth, and the speed is some really tiny speed, and I calculated this to be, instead of 100 newtons, it came out as like 0.01 newtons, let's just say. That the net forward, force towards the center has to be 0.01 newtons. Then you'd have to think, well, this has to be 10.01 newtons forward, right? The tension in the rope would have to be 10.01 newtons. So that what would the net force be? This is like a minus, this is like a plus. The net force would be 0.01 newtons, and we'll be good, right? And then you'd again say, but isn't that more than it weighs? It weighs 10, yeah. No matter what the speed is at the bottom, and the AP exam always will bring to light the question about the bottom of the path. The force will always be the upward force, whatever that might be. And let me point out, it could be the rope problem, or it could be something that's like, sitting on some sort of, this is the rope now going up here. And like my demonstration, which I haven't shown you yet, unfortunately, it's got sitting on some sort of piece of wood or something. If that were the case, though there is tension here, the rope wouldn't actually be, they do draw it this way, by the way, on AP exam. The rope isn't touching the cup. The only thing that's touching the cup is the wood in here, and therefore that upward force would be the normal force. And they could ask the same exact question, and they could say, calculate the normal force. And we would have done it the exact same way we had before, but instead of FT, writing FT, we would write FN. And even in this scenario, the normal force, which again is what a scale would read if you could place the scale underneath that as it went back and forth. That is what the normal force, it's what the scale reads. It would always read more than it weighs when it passes through the bottom point. When it passes through the bottom point, the normal force would always be more than its weight. And so would the tension. Now, again, when we return our attention to the top, let's imagine swinging this around in the giant circle again. This is vertical. At such a slow speed that the rope, so at the minimum speed, maybe the minimum speed is 12 meters per second, meaning as long as this thing is moving in this direction with a speed of 12 meters per second, the water that's in here won't fall out. If you are to actually swing it around with that exact minimum speed at this point, believe it or not, the tension in the rope goes slack just for a brief moment. There ends up being zero tension when bucket is moving at top with the minimum speed necessary to prevent spillage. So as long as it is moving exactly at that speed, believe it or not, the rope goes slack just for a brief moment. A moment later, it tightens up. As soon as it passes through that point, it tightens up again and you get some tension. And this is because, remember that in order for something to stay on a circular path without deviating away from that circular path, the inward force, which is the centripetal force, has to be equal to mv squared over r. It turns out that the force, if the tension doesn't provide any downward force because of what I just said, it goes slack, then the only force that's providing that amount is its weight. Turns out that right at that minimum speed, the weight of the object, Earth's gravitational pull, happens to exactly be, like if this was the 1 kilogram mass, 1 times 10 newtons, turns out that if we adjust v to be just at that minimum speed so this doesn't spill out, 1 times v squared over r comes out as 10. The gravity force is able to provide just enough force in the downward direction, which is a centripetal force, to prevent spillage. That's the main idea. At the minimum speed, there's no tension at all. If it was still on that platform like I talked about a moment ago, it would literally separate. If you're going just at that minimum speed, the cup would literally separate from this piece of wood for a brief moment right at the top at that minimum speed. If it separates, that means there's no normal force. The normal force, by the way, would be pointing down if you're upside down. This is the wood pushing down on it. But if the cup separates, it's wanting to fall out because it's like so dangerously slow, so slow that you see that this has gotten loose. You see the cup is slightly slipped off of this. There's no normal force in that brief moment. But then a moment later, it catches. A moment later, this thing swings down underneath it and catches the bucket, and it continues around. So there's this moment of very brief moment of separation when you are moving at that minimum speed. That's what we're talking about. When you're moving sideways with that minimum speed, there's a brief moment of separation where the normal force would go to 0 and the tension would go to 0 if this was the apparatus that I've been describing. And that means the only downward force remaining is gravity. Turns out that V is just slow enough so that the whole product here of mv squared over r comes out exactly as mg. And for that reason, when we solve this, solving for the minimum speed, remember that the net downward force towards the center, this is the top, the net downward force has to be equal to mv squared over r. That's the centripetal force. The centripetal force is the net amount of force that needs to be pointing in the downward direction. And I've already established that the only force that's doing that would be gravity. So when you write F net equals mv squared over r, in general, as this thing goes around, you might say, well, there is the tension force and there is the gravity force at the top, right? At the very, very top, if there was some tension here, I know I said there isn't, but if there was some tension here, the tension would be pointing down. This string is yanking downwards on that bucket. So you'd have the tension force. Remember, towards the center is plus, away is minus. In that case, you'd write Ft as this would be a plus. Mg is also, at that point, straight down. We're really backing this up a little bit. We're talking about this moment right here. Ft would be straight down, plus. Fg would be straight down, also plus. But again, at the minimum speed, actually the tension in the rope goes to 0, and it separates from the platform that's on for a brief moment. And for that reason, this is crossed out as 0. And now you're just left with mg equals mv squared over r. If that's the case, m's cancel out, which means if you can hit this speed at the top that we're about to calculate, it doesn't matter how much water you have in the bucket. It could be a few drops of water, it could be a gallon of water, it could be 10 gallons of water. It doesn't matter what the mass is. As long as whatever amount of water you have hits the speed, which we're about to solve for, you'll be good. What speed? Well, what's left? G equals v squared over r. This is representing the minimum speed, by the way. The minimum speed to prevent spillage. Solving for v min, we get g times r, or rg. I guess textbooks typically write it as r times g. And therefore, if we square root both sides, we end up with the square root of r times g. Super useful. It comes up on the AP exam, this formula. But specifically this problem of something going around a circular path. And this is referring to just at the top. This formula is only valid to use for calculating the minimum speed necessary for this bucket to have that minimum speed just at the top so that water doesn't spill out. What would R be? R would be the length of this string. They'd give it to you. And G is, of course, 10. And that allows you to solve for what that minimum speed is. And as long as it is moving at that minimum speed, again, there's no tension. There's no tension in this wire. There's no normal force. Those are actually 0. You could certainly go faster. And if you go faster than that minimum speed, which again, if this was a 1 meter, like I had originally said, this was a 1 meter string, then what would it have been? 1 times 10 square rooted. So it would have been the square root of 10, roughly, 3.3 or so meters per second. So as long as you can have that speed at the top of 3.3 meters per second, it wouldn't fall out. Of course, you could go twice that speed or 3 times that speed. You can go any amount of times faster. You can whip it around as fast as you want. If you are going much, 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 much faster, then of course this rope won't be loose. There will be some tension there, pulling in the downward direction if it's going much, much faster than that minimum speed. Even if that were the case and you're going really, really fast, again, remember that at the bottom, the weight will always be more. At the top, the weight could be at the top, I don't know if I messed up my words there. At the bottom, the tension, I don't know if I said that, the tension would always be more. At the top, the tension could be 0 if it's moving at the minimum speed, or it could be scenarios where it's equal to what it weighs. If you're moving a little faster, the tension might be equal to its weight, or even a little faster still, the tension might be equal to more than its weight. At the bottom, the tension is always more than it weighs. At the top, again, the tension depends on just how many times faster than this minimum speed you're going. Usually their problems are about finding that minimum speed, and I've at least now shown you how to do that. All right, that wraps it up. Hope you find that helpful.